Now, I'm going to go through some example wind calculations as well. My first example, I'm just going to take to be as simple as possible. Just an omnidirectional structure. I picked a location in the inner Melbourne suburbs in Caulfield North. As you can see, it's very flat, very uniform. It's just a whole lot of one-story houses all around this. The structure is a perfect rectangle, one story, so maybe average roof height, 6 meters. Relatively steep roof pitch of 30 degrees, but I'm going to demonstrate this by working it through the ClearCalcs platform. So the ClearCalcs platform works by just simply opening up clearcalcs.com on any web browser, logging in, and then I can create a new project here. Every project we intend to be having to do with a particular structure that you are designing. So I'm going to call this webinar example 1. And we can assign project numbers and client names as well. We said that the address for this particular project is 21 Erkeldoen Street. And we can see that this looks up automatically, the address, pulls up latitude and longitude, and gives you the map of your location that you're considering. This is just an arbitrary address, by the way. I just literally was looking at Google Maps and picked one that I thought looked good. So this address has nothing to do with anyone. It is just an arbitrary address. We can then add a wind load calculator. So calculating wind loads via AS1170.2. We'll load you up with telling you what references we're using. So this is 1170.2, including 5 different amendments to it, to version 2011. Some brief instructions. We, in our calculator here, allow you to set the terrain and shielding factors once for just the worst case, or you can set it individually for each direction. After you create the calculator, you'll be able to, we haven't quite implemented this fully yet, but you will very shortly be able to link any loads listed into any of our design calculators for beams or columns. So you'll use this calculator once in your project and then link it into everything else. We do make some assumptions in here, basically the same assumptions as I made in the presentation here, where we have a rectangular enclosed building. Lee wind factors we aren't calculating automatically for you. If they are relevant for you, you can enter them in manually. And we're expecting you to calculate your K factors manually as well. We do give you a number of default values in here as well. For most structures, you are going to have an NCC, design working life. You can change this as well, though. And you can change it to higher design working lives, or if you have a non-NCC structure, such as some particular temporary work structures, may be designed to different working lives as well. You then, we automatically load you up with some default values. But first, you're going to want to select your wind region. This is a Melbourne area structure, and our default value is actually for the Melbourne area. You can see in our map here, if you expand wind region, you can see in our map that Melbourne is highlighted with its own wind region, A5. So you select A5 for wind region. So that the building orientation was 10 degrees. Building width, or excuse me, yeah, building breadth of 14 meters. You're not allowed to have your depth be greater than breadth in most cases in our calculator, just to keep calculations a little more straightforward. So hence you see an X show up there. But if we set our actual depth value here, 10 meters, then that error clears. Average roof height of 6 meters. This is a gable roof that we're considering. And we said it was a 30-degree roof. That ratio of openings from one surface to all of the other surfaces, we set as 0.5 here, so relatively even between all of the surfaces, and largest on the front. We can then set our terrain parameters, and we give you the set Google satellite map of your location right in this calculator as well. So you can hopefully easily look up what all of your terrain categories and shielding factors and such should be. So terrain category, this is very clearly a just inner suburb, numerous closely spaced obstructions or buildings. So terrain category 3. There's shielding buildings in every direction. When you're entering in omnidirectional values like this, you will take your worst case of all directions. In this case, every direction is essentially the same. The important thing is your definition of a shielding building. So 45-degree arc and distance of 20 times h. Unfortunately, because of Google restrictions, we're not able to display the scale here. But 20 times h in our case is 120 meters, or about roughly 10 times the length of the building that's shown here. So that would go out to roughly where my cursor is, a couple of streets out. So we can estimate what the number of shielding buildings in there might be. I'm going to say it's 30. These are all one-story buildings around there, so it's a pretty safe bet that the average height of the shielding buildings is equal to the same thing as the average roof height of the building I'm designing here. So 6 meters equals h. We're allowed to enter in formulas in the calculator here. The average breadth of those shielding buildings, remembering that this is normal to the wind stream. So zooming in a little bit on our map here, note that all the buildings are essentially aligned with an axis in one direction. So if the wind is coming in from the east, that breadth is actually relatively small. So I'm going to say that the worst case breadth here is about 10 meters. Most prominent topographic feature, well, we have nothing here. So whatever we select here is essentially irrelevant. Highest height of hill is 0. So we're in a flat terrain here. And at that point, we're essentially done. We have everything that we need. This is now displaying what your site wind speeds are, what your design wind speeds are, and then the wind loads in every direction in this large table here. As I mentioned, you will be able to link these loads out into any of our design calculators for beams or columns or connections or anything else shortly. We do, just for your reference, give you a class equivalent for AS4055. So while we are designing via 1170, we can tell you roughly what that's equivalent to. So that's roughly equivalent to halfway between an N2 and an N3 in AS4055, so N2.5. Again, that's just for your reference. That's just sort of a fun fact to know, to sort of keep track of where you are for your wind loads. But we do give you that equivalent. If you would like to change any values that you will load link out, by default, we're assuming that your combination factors are 1 and all of your other K values, the area reduction factor, the permeability factor, etc., are all 1. If you'd like to add more, you may. So let's say we want to consider cladding on the walls. I can select wall, any direction for the surface type. Add 1.0 from the combination factors. And the cladding will have a multiplier on it of different things depending upon the different calculations. We are expecting you to do those manually, but we could enter, say, 1.5 here. And then we'll have an additional row added on to this main table here, so that we'll be able to load link out. So cladding wall equal to these pressures for serviceability and ultimate cases. So that's our example number 1. Example number 2, we're going to look at a directional design for a much more complex site. I'll say this is a two-story, rather polygonal shaped house, rather unusual shaping. We're going to say at the front of the building is oriented 15 degrees, so serving the north-northeast direction. We're going to say if there's an openings ratio of 2.0. That's pretty large, but in this particular structure we are in Townsville, just south of Mount Louisa. You might want to have a lot of windows looking out at Mount Louisa. It's quite pretty. So that may have a very large openings ratio. We're going to say that's 2.0 here. So again, this is the Townsville area, so very close to the coast, definitely a cyclonic region. There is one very prominent hill structure to the north here, that's Mount Louisa. To the west, it's very flat, essentially farmland. To the east, it is all shielding buildings, and to the south. And we will enter this in directionally and go through how things look if you're considering every direction independently. So for this, we're going to create a new project. Call it webinar example 2. Project address, we said this was 63 Ellsworth Drive in Mount Louisa. You can see we pull up that same Google map for you, so you can quickly reference where you are. Add a new calculation for wind load. Now, we will shortly be automatically determining what your wind region is. For now, you do need to actually look it up manually. We can see pretty clearly here that the region is this blue region, very close to the coast in Queensland. So that blue region corresponds to wind region C. Again, that is a cyclonic region. It's a normal structure. So it's not a farm building. It's not a mass congregation structure. We're still designing to NCC 2019, and we don't feel like costing our customers more by designing for a higher working life. Said orientation was 15 degrees. The overall breadth was 22 meters. The depth, 17 meters. And we set a roof height of 9 meters. For this, we did have a hip type roof and a pitch of 15 degrees. Maximum ratio of area of openings of 2.0, and that's on the front of the building. Now, we can completely ignore this section for worst case of all directions, or it will be passed down as defaults to our values in every direction. So I'm just going to ignore it for now, and we can enter in everything manually below. So below we have a terrain properties for each direction. So terrain properties, in most of these directions, it's still numerous closely spaced obstructions, TC3, except to the west, we noted that it was essentially open terrain. So that's TC2. Northwest and southwest were something of a mix between those. So we're going to call those TC 2.5, but everything else is TC3. So TC3, terrain category 3, between north and south, TC2 to 2.5 in more westward directions. Shielding buildings, there is nothing to the north because that's Mount Louisa. We're going to say that there are a few of them to the northeast. While most of these structures in reality are one story, for the purpose of this exercise, so that you can actually see what the shielding multiplier comes out to, I'm going to pretend that all of the structures here are 2-story. So I am just going to say the average roof height of all the shielding structures is still 9 meters for all of those shielding structures here. Average breadth, I'm just going to leave at 20 meters for all of these structures. Eastward direction, we have a lot of buildings. So I'm going to put that at 30, same for southeast, same for south. And for southwest, we start tapering off a bit. So I'm going to say those are 10 buildings. West and northwest, there really weren't any buildings there. Now, topographic features actually have an effect on what the shielding multiplier is here. So you'll see actually some of these values change based on what we put in here a bit. So topographic feature to the north, northeast, northwest, we have a bit of Mount Louisa. So to the north, we have about 120 meters in height there. The peak of Mount Louisa is 185 meters. That's more the northeast. For the horizontal distance from the crest to half the height, I'm going to say it's about 200 meters. And distance of my structure, 0 would mean I'm right at the crest. I'm going to say I'm about 400 meters from the crest of Mount Louisa there. So that gives me a hill shape multiplier here. Northeast, I'll enter in some values in here because we still have a significant portion of Mount Louisa. I'm going to say that's actually the peak of it, 185 meters. I'm going to say the horizontal distance from the crest to half the height is still about the same, steepness, but we're pretty far away from the peak of it. I'm going to say that we're about 1 kilometer away from the peak of it. And you'll notice that actually comes up with an M sub H value that's less than 1. We end up taking a minimum value of 1.0. You may have also noticed as I entered that in here, my shielding multiplier changed. It's 1.0 now in the northeast direction. That's because there's an additional clause for the shielding multiplier that says that we can't consider it. It's equal to 1.0 if the slope of the ground in that direction is greater than 20%. So we've checked that. That automatically becomes 1%, or it comes 1.0 for your M sub F value now. And then northwest, we're going to say that there's still some bits of Mount Louisa there. We're going to call it a little bit shorter, maybe 50 meters, a little bit less slope, 400 meter distance there. And then our distance to the structure, maybe 600 meters. Now, if you're actually doing a design, you would check these values a little bit more carefully. I'm going through them quickly, obviously, because this is more of a demonstration, not intending this to be an actual design. We can leave everything else blank there for other directions because it's basically flat in every other direction, and you'll see M sub H is 1.0. Finally, Lee multiplier, only relevant for New Zealand, so it's 1.0 everywhere here. That ends up with our topographic factors calculated in the final column there. So finally, that gives us all of our site and design wind speeds and loads, and pressures. So again, we can see all of our plots here. We can check what each individual value is along our plots by mousing over them. You can also expand any of the calculations in here and go through and see everything that's being done every step of the way. You can see as we combine all the factors for site wind speed, coming up with your V-site data. You can expand out any field that we have to see formulas. So our V-site data, that last column there, is equal to the formula we've talked about, V sub R times M sub D times MZ cat times MS times MT. So we try to be as transparent as possible in all of our calculations. You can see every formula that we're using in every single table here. Figuring out what those become for design wind speeds, we do the same thing for serviceability. Again, you can expand out internal wind pressures and external wind pressures as well. There are a couple of cases where there's some really fine-tuning parameters which you can include in here. Clause 5313, for example, has some special cases for if you have large permanently open vents. So refer to that clause. We include a large description here as to what exactly is in that clause. But you can select yes here if that actually does apply to you. If you don't want to calculate on your own what that ratio of area of openings are, you can input all of your area of openings here and we'll calculate out what that ratio is for you. But within here, we're going through all of the table lookups. We're calculating out what all of your design internal wind pressures are here. Same with external pressures. And we'll do that for both walls and for roofs. Again, you can expand out and see different conditions that we're considering too. So this particular for the external wind coefficient for a windward wall. It's either 0.8 or 0.7, depending upon some conditions. You can expand this out and see if H is greater than 25, it's 0.8. If it's not an elevated building and there are multiple Z values, it's 0.8. If there's only one Z value, it's 0.7. So we're considering all of that along the way. I did not mention if you do have an elevated building or if you have an impermeable building, that's under parameters for special buildings up at the top here. So you can select that you have an elevated building. That will pop out for you what the elevation is above the ground. And we allow you to change those as well. You can also calculate your Z at multiple different heights here. So you can enter in different Z values and enter in as many as you'd like into that table. If you would like to fine tune what your recurrence interval is, that by default, it's 1 to 500 for most category 2 structures, importance level 2 structures. You can also fine tune what your recurrence interval is for serviceability. In many cases, 25 years is a good value. You might want to make that larger or smaller, depending upon your client's desires there. And we do allow you to do that as well. So those are our two examples that I want to demonstrate here. You can feel free to go through our calculators here and see every formula, see exactly a recommended method of going through the AS1170.2 standard. And now I'll finish off with our presentation. Now conclude, and I'll take any more involved questions you may have after this as well. So just to sum it up, compared to AS4055, 1170.2 is more widely applicable, has fewer simplifications. It is a directional procedure, so you're considering 8 directions initially, combining to 4 design directions. And it's one procedure, so you don't have separate procedures for racking or uplift. It's all one. Wind design includes calculating the wind speed based upon the regional speed, a number of direction and topographic features, and the building orientation. Internal pressures, you consider whether your structure is permeable. If it is impermeable, you look straight up in a table. If it's permeable, you calculate a ratio of openings and then look up in that table. External pressures, you calculate 6 different pressure coefficients, three different wall faces, 3 different roof slopes, and follow through the equations shown here as appropriate. And then for final wind loads, you combine the different wind directions, you consider your different K factors here, and you end up with a WU1, WU2, WS1, and WS2 for ultimate and serviceability cases. We performed 2 different examples, one omnidirectional and one direction specific that was more complex. And now I'd like to invite any further questions that anyone has.